I'm recording. If you don't want your voice heard by the whole world, keep your mouth shut.
Sign this waiver.
No, just keep your mouth shut. I'm not signing a waiver. The fact that you speak says that you're okay with it. So, this thing. This doesn't work as well as I would like. I've talked about it twice now. These are not my screws. And they're not loose, so they're clearly not my screws. This is the electret audio sensor. Last time I was telling you it was driving me nuts. It is analog in to an Uno onto channel 0 analog to digital converter. I'm digitizing it at a 8 to 10 kilohertz rate. I've got an interrupt set up in there that just, so it's regular timing. It hits it tick, 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 tick. Otherwise you get this drift back and forth and it makes weird warbly things happen. Then I've got a PWM on this side running at 100 kilohertz. And I'm just taking the value off of this. I'm trying to do some on-the-fly correction and throw it in, so it's really not working as well as it could. And I think maybe my gain's turned down on my mic, and that is a teeny tiny. I have to have like a micro screwdriver to turn it. So, plug it in. Hear the static? So, maybe I can talk and you can hear it and understand it. Could you?
Yeah,
I mean, it's Darth Vader. I can.
I'm not sure what class amp that would qualify.
Yeah. This is a D. This is a Class D amp with a very narrow, very narrow bandwidth and a shitty speaker on it. But it will do the regular. Oh.
Okay.
Yeah, the feedback loop. So, hi, and it'll do. The problem is it actually works better than I thought it did, because I'm sitting in my room, in my office, with a running computer and a running disk drive and a running oscilloscope that all have fans in them, and so I can't hear it at home at all. So anyway, there's that. No amplification, just some screwy stuff. If you're really interested, I've got the ugly code for it. It's bad. As is most of my code. Let's see. Last time we spent 2 hours on temperature sensors. You can feel free to ask anything at any time in the class.
I will.
So my general attempt is to keep the class at about an hour. Usually it ends up going about 2 because somebody gives me a rabbit hole to run down and I run down it. They occasionally go 3.
Yeah, I think the Tom, in a nutshell, could you explain this thing, was 45 minutes?
He was asking not in a nutshell questions. He was asking it depends.
I wanted the super surface deal, but Tom's very thorough. So and Tom, I appreciate it. I really just to let you know.
When I run long and start boring you, let me know. It happens. I know it. So I try to generally put the things I talk about at the maker level. Somebody who doesn't, like we talked about, somebody who doesn't really know the ins and outs, but wants to learn some stuff and maybe has some ideas for some neat projects that they can do fairly simply. I target everything. So far, I've targeted everything when we talk about code and making a microprocessor work type stuff, digital stuff, towards an Arduino Uno. And the reason I've chosen that is $25. And the development environment is free. So if you've got a laptop, a USB cable, an Uno, you can start making lights blink and have a little bit of fun with it. Anything that you guys joining the class?
Yeah.
Have a cookie.
Come on in, there's cookies.
Come on, there's a cookie. Have a cookie.
There, we have a cookie.
We got.
Nice. Alright, well come and sit, and let's just see how it is. Oh yeah, you
Hey, if
come
you,
on over.
if you don't make him, if you don't want to. This is fun stuff, but if you don't want to have fun, that's up to him. If forced fun is not fun. Just ask my kids. So, where was I?
Maker level.
Yeah. So, but what I do is I often go behind the curtain a little bit, and we go into not so much the math, but this is what's going on back there, and to try and give some insights into more than. Because like I was saying, I have a firm belief that if you understand a little bit about how it works, you can make better use of it.
Right.
Maybe, you know, some people don't care, and that's fine. But be careful the questions you ask, because you can send me down a rabbit hole. And I can fill this whole board up with stuff that you don't really care about. So keep me in check. Something else there. This is the other thing. I'm scatterbrained, so I bounce from topic to topic because there's a lot of this stuff that's interrelated. You get on this topic, and you go, oh, by the way, this other thing here, and oh, by the way, and then eventually you close the loop and you're back, oh, yeah, I was talking about this, and this is how that all worked, right? Sorry. Cookies. How can you not want a cookie? Are you sick? Are you sure? They're good cookies. I ate one. You can tell. Look.
This is not.
So last week, and every week, well, I don't know about timeliness. Every video of every class I've done, I've thrown up online on my YouTube channel.
And what's that?
I think if you look up TOMBURKEII, I think you'll find it there.
There's
You'll
links to your YouTube on the Makerspace page anyway.
Yeah,
on the
each of
Makerspace,
event.
on the Facebook on the Makerspace's Facebook page, he posts the links up. He's posted a couple of links. I have a playlist that is just this class.
Yeah, once you started doing the playlist, I just included the playlist link for each class.
Well, but you handed out, I think, one of the playlist links that is my electronics,
Okay.
silly stuff.
Okay.
So I have multiple playlists. One is just this class.
Okay.
One is like learning electronics / electronics, and it includes FPGAs and all sorts of other stuff. And there's 50 or 60 videos there. And so this falls in and doesn't always...
Okay. There's a playlist link on the event for this class on Meetup and Facebook and on the website. It will get you to his channel.
And then you can pick the correct playlist.
And then you can figure it out from there.
And I sat down and I actually listened to, usually within a week at the most 2, I get it up after, because we usually do the class about every 2 weeks, with occasional skips here and there. And maybe I need to show you this. I just got done showing them this. You know what a megaphone is? One of those police horns, fireman's horns they talk into. Why can't I get this thing to plug in? There it is.
Superposition. I've seen it.
So I made this.
Cool. So I love
It doesn't have any amplification, and it sounds awful, but fun stuff that we do. He looks completely unimpressed. So today, I was going to talk about infrared receivers and transmitters, like your remote controls.
Oh, okay.
So back in the very beginning, the very first TV remote controls, I remember my great uncle had one of these. They were actually sonic.
Mm-hmm.
And it had like a, piezo element in it or something, and I can actually hear it. Or I could then.
You could hear it click at least.
No, I could hear it whistle. I can hear the flyback transformers in tube televisions. I just had 2 buttons. It had channel up, channel down, volume up, volume down, and I think inside it actually had a motor that clicked. Because you put it here and you could hear the TV go punk.
Yeah.
But what was also really interesting was I figured this out. I had a metal slinky, and I figured out if I got it the right length going, I could change their channels and screw with them. So clearly, there's trade-offs in the way you do these things, right? So Sonic, great, but there's a lot of noise in the environment. So let's, and there's often a lot of loud noise in the environment that's going to swamp out, it's going to be louder than your thing, right? So you could go to a radio frequency, but you know, these go back a long time, and radio frequency would have made the remote control as, you know, like this big to be able to control your TV. Light emitting diodes were new, and they worked. And so you have, we're going to get into a couple of things. This might, the last time I said this is going to be a quick class, it went longer. So we've got a, I've got some guy sitting here in his Barca lounger, lazy boy, and he wants to change the channel on his remote control, right? And over here, I don't dare draw this with a tube in it, do I?
I was going to say, is he going to draw a square or a really thin rectangle?
Over here, you got your TV sitting on the dresser and the cable box sitting on top of it, right? Because nobody changes the channel on their TV anymore. You got to change the channel on the cable box. And so you want to send a signal from here to there to make something happen. Well, okay, we already discussed why we don't use RF, because it would have been huge given the technology at the time, and not work very well. So let's put an LED on this end, or a light. Let's put a light bulb on this end. An LED is a light emitting diode. This is the symbol for it. And I'll push the button, and light will come out, and the light's bright enough to be seen from over here. So I put some, if you look at the old ones, they actually had like a lens on them. The original ones had a lens on this end to pick up more light. And I think they actually used like 3 or 4 LEDs. So you could have 4 LEDs. I could send out red, and that would be channel up, and I could send out green, and that would be channel down, and I could send out blue, and that would be volume up, and I could send out, I don't know, maybe 2 of them at once, yellow and blue, and it looks kind of orange. Or inside the guts of that thing, it says, oh, I see both of these at once. That means I should do this. Channel, what's left, volume down. And that works in a dark room. Now I've got a light bulb up here. They were all incandescents back then. But they don't flicker too bad. These flicker faster than your eye can perceive it, but if you ever point a camera in a room, you can watch if you do it right, you can watch the room flicker off and on in the thing, because all the lights are actually coming off and on together at 60 times a second. Actually, I guess 120 times a second, both sides of the cycle. But maybe only 60 times a second. But with the right kind of cameras, this whole room just, because you get this thing like when you fire a strobe light at a ceiling fan, or if you're driving down the road and you're looking through the divider between you and the other side, and you see the guy's wheels looks like they stopped turning. It's because you're chopping them. You're chopping the picture at the right frequency that you're seeing it at a certain state every time. And so it looks like the wheels stop, or maybe they start to go backwards. You're taking a picture in your room, and people are flickering on and off and disappearing, and it's crazy. So we got a flicker problem, and also, if you're like my house, the wall's here, and there's a window right here, with the sun out here doing its thing. Looks like a fish. And now it's shining in, and it's screwing up this thing. So now I'm putting so much light of every color into there, it doesn't know what to do. There's your first problem with the remote, an optical remote control. All this other light's going to ruin it. So what do? Well, if I look at the color spectrum from the sun, this is I think Planck. Last week I said Sebring effect. It's the Seebeck effect for thermocouples. This is the Planck blackbody curve for temperature. This is 0 degrees Kelvin, and this is infinity Kelvin, and it looks like that. And this is yellow, green, blue, red, violet. This is the if you look at the sun with a spectrometer with a prism, these are the colors that you see. And then over here where you can't see is ultraviolet, and over here is infrared. And then, so if I break this up into wavelengths of light, this is about 500 nanometers, I think. That means there's the wavelength of that electromagnetic, light is an electromagnetic wave. The wavelength of that wave is 0.5 billionths of a meter. Teeny tiny. And blue light is over here around 450, 400, maybe down. You might be able to see as far as 380. I think around 350 is ultraviolet.
I think the blue-violet laser I was 450.
The 450, maybe I'm off. Maybe this is 600. Because that's about right. Because this is around 800 or so here. Bye bye. Have fun.
Thanks.
This is the deep red, and then out to about sorry. Oh, that's my mom. She's not there. She's in Indiana. Out to about, depends on who you talk to. There's near infrared, there's shortwave infrared, there's midwave infrared, and there's long wave infrared. No, let's see, that's temperature. Temperature in Kelvin, and this is light emitted. Energy. So, if there's something this hot, it doesn't give off anything. As it gets warmer and warmer and warmer, actually, I'm sorry, this isn't 0. This is like stupid. I've got this backwards. 0 Kelvin's over here. You give off no energy, you give off no energy, you give off no energy. Now things are hot, and you're giving off thermal energy, and you're not. That's not true. So we talked about this a little bit with the temperature sensors. An atom moving is heat. The only way you get to where there's no heat is if you get to absolute 0, which we've not been able to do. That atom sits there and starts to vibrate, and when it vibrates, that's heat. If you have a bunch of atoms together all vibrating, the average, the integral, the total of their heat is the temperature. So down here on the ground, it's warm, but if you go in and you got but it's warm, it's actually fairly cool, but you got these atoms that are moving around and bouncing off of you. Hot air goes up into space, right? So you go up into space, but it's cold. What's going on? Well, yeah, the hot atoms rose up out of the thin ones. They are cooking. They are moving fast. They are really hot, but there's so few of them that the total temperature's 0. It's an integral of number of whole things. So you can have a bucket with one really, really hot atom in it, and it'll have 0 temperature, or you can have a bucket with 500 quadrillion billion, only a little bit warm ones, but they'll feel warmer than, they'll have a higher temperature than the one out there as an aggregate. So you get to a certain point, you start to emit. You and I, we are emitting energy. And what's happening is, as these atoms Light is emitted because an electron goes from one state down to another, and a photon is emitted. That's where light comes from. It's that simple. You're moving around all this heat. These things are jiggling all over the place, and one of these electrons goes whoop, whoop, and then falls back in. Boom, it gives off. Down at those low temperatures, that photon has a long wavelength. It does not have much energy, so it's got a really long wavelength. You get up here, if I've got the energy, the same amount of energy here that gives me one blue photon will give me like 10,000 infrared photons. That same amount of energy. That's why blue light gives you sunburns and breaks your DNA and gives you cancer. Because it's high frequency, it's high energy. Loosely. The other thing I'll say is I lie a lot for simplicity's sake. So now there's a little hump out here in the mid wave and the short wave and there. Now all of this stuff, we don't go way out there. It makes perfect sense to go and put our detector out there, right? Because there's no energy out there that's coming from the sun. It's only going to be things that are hot. Well, that's the first problem, your room's hot. But these are really expensive materials. This is indium gallium arsenide, this is mercury cadmium telluride, this is also mercad. These are platinum silicide. These are things that have long names that sound really expensive, and they are. And so we never went there. And even now, even today, after 100 years of this, good detectors out there are still expensive. And you'll spend, I've seen detectors that are thousands of dollars.
And they're not real pleasant materials to be around.
They're not pleasant
either.
materials, and because you are, because heat is given off at this temperature, you got to keep them colder than the temperature that you're at. So you got to cool them. If you want them to detect something, they have to be cooler than whatever it is they're trying to detect. So if it's in your, that doesn't seem like much, but now your remote control has to have a cooling plate in it and a power supply off the wall and its own air conditioner. This band, though, right here, from about 900 to 1100 nanometers, near infrared, silicon works. Silicon works pretty good. We talked before about, I'll go over it again, how a photodiode works. I've got a piece of P-type and a piece of N-type silicon. The way I get these is with doping. One's arsenic, another one's boron. I don't remember which one's which. And it's actually the same piece. They're not glued together. It's the same piece of crystal, and I do the implantations differently on the different sides. And what happens is it creates a barrier region here. This is heavily N, so it's got an excess of electrons. This has an excess of protons. The P's will want to jump over here, the E's will want to jump over there, and I get this barrier region where everything is filled up and happy. And if an electron should happen to come into here, it'll immediately get swept over to this side. And if a proton should happen to come in here, it will immediately get swept over to that side. What happens is you get an equilibrium, and this is called, not your diffusion depth. Yeah, it is. It's I can't remember what that's called. I want to say diffusion depth, but I know that's not right. So now, this is a system with two wires that is at equilibrium, so nothing's going to happen. But now if I have a photon come in, and this little atom right here with his electrons running around on him gets hit and absorbs that photon, that electron pops out. That electron immediately gets swept off that way. If I put just a little bit of a bias on this thing, it's going to make them want to go that way. That's how the photodetector works. It's made out of silicon. What's silicon made out of? Sand. It is the most, I think it is the most abundant element on the Earth. You take it, you melt it, you turn it into a crystal, you throw some other stuff on it. They figured this out in the 40s. I guess they actually figured out in the 20s. They figured out how to do it in the 40s. They figured out how to do it good in the 60s. And they've been getting better at it ever since. So, let's choose this band right here. Down here, this low spot, this is not much energy. Now, the problem is my silicon has a sensitivity that looks like this. So that means my piece of silicon is still going to pick up all of this. So now let's put a filter in front of it. I'm going to draw this as a filter. I don't know what else to do. This is an optical filter. It's red, it's green, it's blue, right? If I use a green filter, it only lets green light through. Well, I don't want to use green because there's a gob of this coming from over there, so I choose an infrared filter. For me to sit here and look at it, it looks black. If I hold it like this, so I'm looking through, it'll look almost like a mirror. I'll see all this stuff back here because this is going to reflect off of it and not go through it, or it's going to be absorbed by it. If it's an absorption filter, it just gives up all the rest of that as heat. It's a reflective filter. It's called a hot mirror, or actually a cold mirror. A hot mirror reflects everything that way, and a cold mirror reflects everything that way. So it looks like a mirror, but it's transparent to infrared light. And if you, I should have brought one of those today. If you take apart a little camera, a little digital camera, if you pull the lens off of it, you'll look inside. There's a little square chip on the inside of it.
Yeah,
that's
the
the infrared.
sensor.
That's the infrared. No, that's the infrared filter. On the lens side.
Oh, on the lens side, yeah.
Yeah. If you look at those little El Cheapo cameras, you'll see it looks like kind of like this. And there's a lens right here. And this has a cavity in it. This is threaded so they can adjust the focus, and then they put a drop of glue on it or something to freeze it in place. And then your image sensor sits right here, but right there is what looks like a little piece of glass. That's an infrared filter. If you take that out, your pictures will look a lot different, because silicon is still sensitive out here where we can't see.
Yeah, some people will take them off to make them night vision cameras, quote unquote.
Yeah.
Which works, but it also degrades your normal image quality.
Well, you can get some interesting effects out of it, and if you've already calibrated out what red, green, and blue should look like against a test pattern, then when you throw the infrared on, given some certain assumptions, you can pull the red, green, and blue back out and see only your infrared. And you can get pictures of what the infrared background looks like, and that's cool. But still, it's near infrared. It's not emissive, so it's not really night vision.
Right. But if you have an illuminator, it helps.
Right. If you've got an infrared LED, you can use a. Anybody got a remote control? Is your setup to do a remote control? Mine's not.
I don't. Actually, my old phone was, not this one.
You can point it at a regular camera,
Yeah.
and you can see it on your TV screen. Because it's bright enough that enough of it makes it through that filter to get into the rest of the stuff. It's a great way to test to see if your remotes are, this shit's not working. Is it because I lost a program or the battery's dead? You point it at a TV, point it at a camera and look at it. So now I have put in this notch filter, this bandpass filter that's only going to get light through right here. And these are pretty narrow. But there's still light in here, and there's a multipath effect. I point it here, and bounce off the wall, bounce off that wall, bounce off that wall, come back here, and it'll hit the button twice. It'll get a bright signal, and it'll get a dim signal, and you'll be sitting there holding volume, and you'll let off, and it'll keep going volume for just a teeny little bit, and it'll be too loud, and you can never get it right. I've had one that does that, and it's frustrating as hell.
So you just put a really quick clock cycle for receiving.
Close. Close. Next trick we do, so you've seen that sort of red front that we put on them, because the diodes are tuned to, the diodes are generally tuned to the frequency. You can buy a 800 nanometer, an 850 nanometer, a 900 nanometer, an 1100 nanometer diode. That's their center. They have a tendency to look like this, with that being their center and then a quick fall off on either side. And sometimes that's not symmetric, sometimes it's more one side than the other. So they put this extra filter over the top of it to kind of give you a little bit more of a chop there. And those are funny. It amazes me that they block anything because they look red to me, and it's like, well, they must be letting through a little bit of visible light too. So now the next thing we do is we say, oh, well, I've got all this weird stuff. I've got these multipaths going around. I've got the sun flickering. I mean, you know, a cloud goes in front of the sun, or a bird flies by your window and your TV channel changes. I have seen an old TV set that would happen to. You'd be like, what the hell? Once we figured it out and we knew what was going, turn the TV a little bit or whatever else. But so what we do is we encode our signal. So now I'm only using one color, and I want to send codes, right? So I can just send, we talked about RS-232 and serial signaling a long time ago. I can send an 8N1 serial code, and I can say, you know, here's my start bit, and I can send 8 bits, 1, 2, 3, 4, 5, 6, 7, 8, and a stop bit. So I'll send a start bit, and then I'll send a 0, 0, 1, 1, 1, 0, 0, 1, stop. And so I just sent this code, I think. 2, 3, 4, 5, 6, 7, 8. Yeah, I just sent that code. Start bit, stop bit.
Okay, so instead of on the receiving end truncating it, you have it just finish after 8 bits on the transmitter.
Right, but what happens is when you get these weird multipaths, so usually what will happen is you push it and it'll send it like twice. Just error checking, right? The far end will look at it and say, oh, I got it twice. It's really what he meant. Or 3 times, you know, because this goes out so fast you can't take your thumb off that quick. So with that multipath, what could happen is by the time the second one gets there, this could have come back around and been here. So now I'm using one LED, but I've got 4 things I want to say, right? Channel up, channel down, volume up, volume down. So I can send that with just 2 bits. By the time I send that around the second time, or if I've let my hand off, the microseconds that it's taken to go around, nanoseconds that it's taken to go around the room, now I've got this first bit is actually walking over my last bit or whatever, and it's confusing things. Does that make sense? Am I saying it?
Not in the right time frame, but yeah, I get what you're saying, but
It's fast. It's fast, and
Well-
it depends on bounces and all sorts of other weird crap. But
Yeah, it is light. It is.
it is fast. It's this far in a nanosecond. I mean,
yeah, thank you, Gracie.
it's a nanosecond per foot. So, you know, 15 feet, 30, 45, 60 feet, 60 nanoseconds later, and if I'm doing 9600 baud, that's,
You're not even into the first bit.
yeah. So it happens. There's weird crosstalk that happens. So what they do is, gee, we're having problems here. What they do now is, they do this. When you mash the button, you apply a square wave to the LED at, I'm going to use 100 kilohertz. They put a 100 kilohertz square wave on it. And then they encode that with on-off keying to get the digital signal out. This does two things. This gets rid of part of these weird multipath weirdness problems and flickering lights from something else, because now you can put another filter here. So this light comes in, we got broadband light coming in like this. Here you got narrowband light coming in like this. And now you put a high pass filter on, or a band pass filter that only lets through 100 kilohertz. Now what you get here is the serial signal. So this is interesting. This is hard to build. Up until about 10 years ago, you had to build that all yourself out of discrete blocks. Maybe 8 years ago. I started seeing the first modules 5 or 6 years ago. Started being able to buy these. 5 or 6 years ago, these were still $15, $20 a piece. I picked this up at Micro Center the other day for $10. That means I've got $3 worth of packaging in there and 50% over, 300% overhead. That means this thing costs less than $1.
Where's the Micro Center?
There's a Micro Center up in Towson.
It's one in Fairfax, one in Rockville. They're all about an hour from here.
Yeah.
Roughly top of the Baltimore Beltway.
Yeah.
Yeah, it's not too bad. It's like an hour drive.
Alright.
Yeah.
It's actually up by where she lives. She drove down here from there.
Jeez.
Yeah, so if you follow her home, you'll be right there.
It might be a little weird. But,
I think if you're looking for electronic stuff, the one in Towson is okay. I think the Fairfax and Bethesda ones actually have a little bit better selection.
do they? I've never been to one of them.
Yeah, we tried to make a point of visiting them just to evaluate, since they're all about the same distance.
Okay, now, so this is the behind the scenes for this guy, for the most part. Now that they've come out with these, this is all easier, because this thing, what comes out of it, you got a power and a ground, and you have the final signal coming out. So whatever went into the remote came out of whatever the controller is, just poops out the other side here. There's two versions of this. It could be inverted. So if you put a 1 in, it might get a 0 out, and if you put a 0 in, you might get a 1 out. It depends. You have to go and look at the data sheet to find out for sure. There's some other things you got to look at. And this is where you can get into, why the hell won't this work? So we talked about, well, I shouldn't have erased this one. But I'm going to erase them all anyway.
Tom, did you want to go over the online places for buying sensors and stuff again for him?
Oh, sure.
Ada fruit.
In order of expensive and what you want to buy.
Adafruit, SparkFun, Mouser, all electronics.
Adafruit, SparkFun.
DigiKey.
These guys are maker
Right.
places. You go
Definitely,
there,
definitely a premium.
you're paying a premium. Those are like going to Radio Shack. But you're going to find something that's already in a package that you can use,
Right.
and it's easy.
Adafruit would be like Radio Shack in a really upscale neighborhood.
Yeah. A Whole Foods Radio Shack.
Yeah.
So
But you get tons of tutorial videos and lots of like little support boards, breakout boards, and stuff.
There's a
already.
lot
Right.
of hand holding.
Arrow,
they've got a lot to it.
Yeah.
Arrow, Newark,
Oh yeah.
DigiKey,
Can you buy them on Jameco?
Jameco,
Okay.
and a few others.
Yeah. Mouser, all
Mouser.
electronics.
Even Amazon now.
Yeah.
Well,
Depending on who's selling it.
I'll put
Amazon will
I'll
link
put
to one of
Amazon up
those.
here.
Yeah. It's one of those.
These guys right here are more, and maybe Jameco. Jameco's kind of a weird bird. I'm surprised they're still in business, to be honest. These are more maker, and these are more EE.
Right.
And isn't there?
I'll just buy parts from them.
Right, you just buy a part. But
Yeah.
DigiKey, hands down, for the longest time, has had the best search engine for finding stuff.
And they still
I-
have awesome.
Well, I was going to say,
Databases.
isn't there Octopart is a search engine for parts?
Octopart is a weird bird.
Yeah.
Octopart is a database that I think has actually been bought by Altium. And they
haven't
use
looked at
it.
it in a while.
Well, it is not user friendly.
Right.
You have to know the part number. But if you
Right.
go in and give it the part number, it can give you the part, it can give you the price for each one of these guys.
Right.
It can give you a 3D model for your CAD if it exists.
Right.
And it can give you the footprint for it, if somebody's made it.
It seemed potentially useful, especially if you couldn't find a part on one of your normal
Oh, yeah.
suppliers.
I'll tell you where it's really useful. I use a tool called Circuit Maker for my PCB design. Circuit Maker is made by Altium.
Is that on Linux too?
Circuit Maker?
Yeah.
That I don't know. Yeah, you have to look. So Altium makes Circuit Maker. Circuit Maker does everything that. Well, that's not true. It does a lot of the stuff that Altium does. It's a stripped down version of Altium. It's number one, free. Number two is you can't store your stuff locally. It puts everything out on the cloud. So if you're wanting to do something proprietary and you're going to make $1 million off of it, you might not want to use that.
There's no
Okay.
private option.
There's no private option. But what's neat is it loads it. It's got a combination of schematic editor and the PCB capture with a halfway decent auto router. There's no such thing as a good auto router, but this isn't the worst one I've ever seen. It will do up to 14 layer boards, I think. I know it'll do 10 layer boards. The auto router doesn't work worth a shit doing that. That's still pretty manual, but it does some neat stuff like phase matching and it can do some other little things. But the thing that I like about it most is I'm designing this board, and you're designing a board over there that's not this board, but it's got, I don't know, that connector on it. You're like, the number one thing that you spend time doing when you're designing a board is making new footprints for shit that you've used 100 times
The
before.
library.
Measuring. Yeah.
Circuit Maker has Octopart pushed into the cloud for a cloud library.
Okay.
You've made this thing, you've got the part number, whatever, from DigiKey, whatever. I go in on mine, I look at it and I say, gee, I need a USB micro connector and boop, 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 boop. And then what I'll usually do is I'll go through, I look at them, they're all the same, they're all about the same cost. So I'll go through and look at them one at a time. If there's 50 of them on there, I'll see which one comes up and somebody's already done a footprint for. Now it's up to me to take a look at that footprint and say, yeah, that's a valid footprint. They did it right. But even that is easier. It knocks
Saves
my
time.
time down by half to make freaking footprints for it, right?
Right.
So it's for this use, it's a powerful tool.
Now, what do you search by?
That's the hard thing. You
Just like SKU or something like that?
by the part number
Okay.
usually.
Circuit Maker?
Circuit Maker,
By Altium.
one word, I think. I don't. It's available on PC for Windows. I don't know if it's available for anything else.
Right.
I used to use free PCB and I used KiCad, however the heck you pronounce that.
Oh yeah, I tried to get into that.
It's a good program. A friend of mine swears by it and uses it all the time. But about the time I was starting to learn that and starting to build my own libraries, I found Circuit Maker came out and they made it. It was a beta at the time. I'm like, I'm gonna try this. I haven't gone back.
Is Eagle another one?
Eagle,
Eagle's free, but it's got like that tiny board, and you've got so many restrictions to it.
yeah,
Right.
and its libraries aren't. They're closed too. You find yourself in the same thing. It doesn't matter what you go to, you end up spending all your time making your new libraries, except Circuit Maker.
Cool.
There are times where I've had to make one. Oh, they don't have this part, but I can go out and it'll let me take somebody else's part that's got the exact same footprint and pull it over. And now I've got this part number with that footprint. Put it out, it goes up into their cloud, now everybody can use it.
Cool. That's pretty nice.
One other plug for DigiKey. Their shipping's awesome.
It's expensive as hell though these
It's
days.
expensive, but
Their shipping starts at like $10.
yeah. And
But
when they list parts, they list it by, as a group of parts, possibly from different manufacturers with all the different parameters for a part, and mostly, usually, they'll let you search or filter for a given parameter across their entire list. So if you want something with a gain, a transistor with a gain of this, or a fan with a noise figure, or a CFM of that, you can literally say, okay, show me just those.
show me something that's, I want fans, here's all the fans. I want an enclosure fan, it goes down. I want a 3-inch fan, bang. I want one that's 10 cubic feet per minute, bang. I want one that's
Runs
got
on
this many,
solar light, you know?
12 volt fan or a 5 volt fan, okay.
Okay.
And-
Oh, and you found the one you want, and it's $700. Okay, well I'm gonna go back and I'm gonna try a different search.
Now, or now I'm gonna look for that at a different place. But for finding part number for something that you approach parametrically,
They also have very good tech support. They've got a couple of decent electrical engineers or technicians at least of different backgrounds. I've gone in, it's like I need connectors. I know I want something that looks sort of like that, but I don't know what the hell it is, and I need to have both sides of it, right? But I need to have it a little bit denser. And I start telling them what I want. I say, yeah, I'm looking for maybe a 100 mil pitch, 37 pin. Yeah, that's a weird number. Well, okay, well we've got this and that and the other. I was looking for one. It was I need 8 pins on the connector, but they have to be able to carry 10 amps each.
What are you making?
and rather than, you know, waiting for the amp representative or whoever to, you know, be in your area, you can talk to them. They're pretty good.
I was making a motor controller.
Really big motors.
I was pushing 40 amps. I ended up using it. They're 4. Each pin can do. Each pin can do 40 amps. I think it's a 4-pin connector on that one. So yeah, that. So where were we? We were talking about. Okay. So I was going to get into where you run into problems with these infrared transmitters and receivers. You can buy. Go look at DigiKey, for instance. Infrared LED. IR-LED. The range can be anywhere from like 850 to 1100 nanometers. That's supposed to be an N, not an M. Usually your numbers are, there's like 850, 860, 900, 910, around 950, I think, 1,000, and 1,100. There's a choice. They're all different prices. They're all, you know, and you need cone angles, all this kind of stuff. But 1, 2, 3, 4, 5, 6, 7. That means there's 7 different light frequencies for this that they could use.
So don't have 8 remotes.
That's actually one. So this is one of the reasons why you got so damn many remotes, right?
Right.
Because this remote's not going to run that TV. You know why this remote won't run that TV? That's one of the reasons. And this is the handshake problem, right? If everybody goes around and shakes everybody's hands, that's 1, 2, 3, 4, 5, 6, 7 factorial. 7 times 6 times 5 times 4 times 3, whatever that number is. It's a couple hundred combinations. The next thing you got to look at. Remember, we're encoding it with our digital on top. This frequency. This one's nice. It says it right on the front. 38 kilohertz. That signal's 38 kilohertz.
Is that standard?
That is a standard. 38 kilohertz. There's a couple of these standards too. It's 38, 50 or 60, I think. I think there's an 80. I'll put about, and there's about a 100. So there's 4 different standards for that. So now, there's between 3 and 5 that are really common. I don't remember what they all are.
Now, are those just standards for crystals or standards for the receivers?
It's for the receiver.
Okay.
That's all built in down in here. That they've got all that built onto.
Okay.
You see that little black square with the little lump on top of it?
Oh yeah.
The lump is the infrared filter that's also a lens, so it's got a wide angle. And then underneath of that is the sensor, and then off on the side, probably underneath of that sensor, is the electronics that'll do all of this. So it's just that little bitty thing that's that big. And if you go to DigiKey, you can buy them not even on that board. It's just a little three-legged device that looks like one of these temperature sensors right here.
Right.
And usually the flat side is the side that's sensitive to the light.
Now, does that come with the encoder, decoder for
No.
whatever bits you want to send?
No,
Okay.
no. What you get is you have to encode your LED with 38 kilohertz at 910 nanometers, and then you put a code on it, whatever that code is, and you will see exactly that code come out the other side.
Oh, so it chops it for serial?
Yeah, it looks like a serial.
Okay.
It's a serial. It's a serial line.
All right.
And now on the back end, now you got to do with it whatever you're going to do. So it's something I've done is I've got my microcontroller here with a SPI, or actually I didn't use an SPI, I used RS-232 into an AND gate into an LED. And this was timer something or another, set to 38 kilohertz. That's how I encode my signal. I put it in, it's an RS-232 code out. Back here on this end, I've got this little receiver doohickey. Black box. And coming out is RS-232 that I just run into a microcontroller. Here. And now I've got a wireless link that'll go across the room. It's actually, I've done it and made it work, and it's also a project that I've got backburnered right now. It's a shooting gallery. Get your little toy gun and you go bang and the thing lights up.
Right.
It's that. Toy gun sends out a code, says I'm gun 1. This one over here says, oh, gun 1 hit me.
Random, but way back in the day, I don't know if you grew up in this area or
Nope,
around. So
900 miles away from here.
might have heard of Photon. It's basically laser tag, but indoor.
Oh yeah,
in
yeah,
an
yeah.
arena.
I've played laser tag here, yeah.
So the home laser tag kits were what you're talking about, transmitter, receiver on the target.
Yep.
Photon did it the other way around because
Yeah.
they needed real-time scoring. So the gun was the receiver, the suits gave off the signal, and then you had a barrel inside the gun to keep it focused, so you were only picking up the signal, what you're
Yep.
pointing at. But
Yep.
then the suit would relay back saying, I hit so-and-so. Made for a real interesting thing, even at, I want to say the first unit was 900 baud, and then they upgraded to 1200. Slightly
Yeah,
less
that's
delay.
actually that's actually what I'm doing. I'm doing the reverse of that. So
Yeah.
I've got my gun barrel here with the LED right back here on this side, and it's a black barrel, so it becomes a soda straw. It only points this way, and then over here I've got the receiver. And each gun inside of it, it has just a couple of switches that you set that tell you it's gun 0 through gun, I think 8 is what I chose. And so it actually sends a code that says bang, 0. It's ASCII. It sends an ASCII code bang, and that's my head. That's my header, so that I know that that really was something talking to me, right? That it wasn't just some noise out there. And so I get bang and then the gun number. So bang and the number 1 through 8, and then I think I put an exclamation point at the end of it. And that's my message that I send. And on this end, it comes in, it hits, and it says, did I get, it just kind of keeps shifting in data all the time. Did I get bang? I got bang. What's this number? It was gun one that shot me, and then this stuff echoes back.
Yeah, I think they did it the way they did it because you also had a helmet with sound, so you would get real-time feedback
Oh,
that you,
yeah.
that you hit somebody without waiting for it to go out to the central computer and come back to you and tell you, yes, you hit somebody.
Oh, yeah.
Because the delay was much longer. The 900 baud was between the suits.
I think the optics works a lot better the way the Photon did it as
Yeah.
well.
It could.
I mean,
I've set this up on a small, like this far, and it sort of works.
well, I mean,
You know, but
Yeah.
what I wanted to do is set up.
I
Like
don't
a
want to
little
hit the sensor, I want to hit the person, and I don't want to cover him with sensors.
Right. So what I
Yeah,
wanted to
this
do
was
is like
better
that.
A couple LEDs makes it a lot easier.
Right. Well, what I want to do is, yeah, right, because you got lights all over you that way. What I want to do is the equivalent of Bass Pro Shop, where you've got
Yeah.
a little thing this big that when you hit it, it goes bing, 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 right? And,
Right.
and yeah, that was one of these things I looked at. There's two different ways to do this. I can have the gun receive it and come around and
Yeah.
come in and light it.
There's reasons for both.
Yeah.
You might be amused that one of the tricks was coming around a corner, and if you were too close to someone to get that shot off, you'd do this and reflect it off your hand. So, like, right up on their chest, be like, "Bip," and you could get them.
I just looked up, says the learnable remotes do a maximum, typically maximum of 32 bits at about 4 kilobits tops.
Is that what they're doing for? So it's basically 4,800 baud.
Yeah.
Because that
Or
'cause-
less.
Yeah. Well, they're-
Usually much less is what they say.
Yeah. So 2,400 baud.
But
Maybe.
they have to account for whatever the manufacturers have done to be truly universal, so they cover that spread.
Yeah, I don't know what they send down. I think I was choosing. Yeah, I think I chose 4,800 baud. So I wasn't going to try and get too speedy with it. I know better. And that's pretty much all I had planned to talk about tonight. I actually got done in an hour. How about that? Open up for stupid questions and not stupid questions and whatever else.
I got one. Probably just an incorrect fact on my part. I thought, I heard, I understood, whatever, that plastic tends to block IR. And yet every remote has a plastic cover on it, you know, for both the sender, both the transmitter and typically the receiver. I don't think they're, you know, replacing that little wedge with glass.
1,000 kinds of plastic
Yeah.
is one
Yeah.
thing.
That's a huge family.
Yeah, it depends.
Material.
It depends.
There's plastics that are transmissive. Okay.
Yeah. If you go up to the National Electronics Museum, used to be the Historical Electronics Museum, they've got a neat little demo there that's got a regular camera and an infrared camera side by side looking at you. And you go in, you press the button. It doesn't work as well as it used to because the plastic's all beat up, but it had a sheet of black plastic and a sheet of clear plastic. And the visible camera could see you through the clear plastic, but the infrared one could not. It's a thermal infrared, could not see you through it. But when you rub your hands and step behind it, you'd see your legs appear or whatever in behind the black plastic, and you'd disappear in the visible camera. So two different plastics, two different
Transmissive.
trends. You get what's called a transmissivity curve. You get something like wavelength out this way, and you get this is 100% transmission, and you get something that looks like this. That's what the atmosphere looks like, right? I mean, not like that, but I mean, visible light gets through just fine, but certain wavelengths don't. An interesting thing is if you have a 2.1 shortwave infrared, I think it's 2.1 micron light. It can be the darkest, dreariest night you've ever seen with a new moon, so no moonshine of that kind. And a 2.1 micron imager will see it just like a full moon. And that is because of sky glow. That's because of all the energy coming off the sun and whatever hitting the atmosphere and causing it to glow like a fluorescent light. It glows out at 2.1 where we can't see it. But with a 2.1 imager, things look weird because
Yeah.
you can see down into your skin at that level. It's things look. I looked a lot older, a lot earlier. Looking at that, but
It's surprising we didn't adapt.
no, yeah, there's things like that. And I'm like,
Yeah.
yeah, and like I said, you got that little lump out there at the one, but 2.1 sky glow. I think it's 2.1 sky glow. There's another one out there that's real similar, but I can't remember what it is off the top of my head. I think around 2.5 is where you start to get really sensitive to thermal. At 2.1, you've got to cool the sensors, but you start going beyond that, and you really got to cool the sensors and cool your optics. Have I bored everybody to death again tonight?
Good stuff. Always interesting.
So that was all I had tonight. I've got, do I have, can I get there from here? What am I going to do for talk about what we might talk about next class? It's on Google Drive. Where's Google Drive?
It's just called Drive on
There it's now. Oh, there it is. Drive. My Drive. Projects. Class order. So what have we talked about? We've talked about analog to digitals and DACs. We've talked about Ethernet. We've talked about SPI and I2C. We talked about temperature sensors. So next, we were going to talk about LCDs one time, but I was trying to make it work with the Ethernet shield, and I couldn't because the Ethernet shield was too tall. So we can talk a little bit about LCDs.
Oh, I got a suggestion.
I can talk about GPS. In my plan, what I've got right now is LCD, GPS, and NeoPixels.
Cool.
I'm open to suggestions.
The difference between CMOS and CCD for cameras.
Oh God.
Well, okay.
So I'm gonna start you off with, my last job I was CCD front end guy. So we can go really freaking deep into that rabbit hole.
Okay. I mean, I know a fair amount, but I'd like to know a little bit more.
Sure.
You're
How late
in
can you stay tonight?
Radicon and Fairchild.
And E2C and Northrop
TI.
Grumman and Honeywell and Kodak and
Oh,
I can actually get down into the physics. My master's electrical engineering thesis, I designed a vision chip that was a CMOS chip. So yeah, we can go really deep into that subject if you.
Well, because I'm not sure, if I'm interested in electrical engineering, I'm not
Right.
sure what flavor, if I want to do photonics or power systems or, say whatever. So I got to try out each one, see if it's more interesting than the last.
Sure. Yeah.
do you like being killed by what you're working on?
Yeah, still.
I am a diver, so
Well, that's
at any point I can.
it's a
drown.
reasonable question. If you do, then maybe power systems are your thing.
I turn that off.